Last section in chapter 5, 5.5, Poisson probability distributions. The Poisson distribution is a discrete probability distribution just like binomial distributions are. It applies to occurrences of some event over a specified interval. We have a random variable x. It's the number of occurrences that happen in that interval, and the interval can be time, distance, area, etc. Just like a binomial distribution had its 4 requirements, bins, they had to be binary, independent, have a fixed number of trials, and the probability of success was constant. Poisson distributions have their own set of requirements. We remember them with the acronym ORION. O, the random variable x is the number of occurrences over some interval. R, the occurrences must be random. They must be independent, and they must be uniformly distributed over the interval. So for example, for a recent period of 100 years, there were 93 major earthquakes in the world. Assume that the Poisson distribution is a suitable model. Part A, find the mean number of major earthquakes per year. Well, we know that there were 93. We know that that was taken as a measurement over 100 years. That means that on average, there were 0.93 earthquakes per year. That's the only thing we need to use this equation. That's going to go where mu is in this equation. And then we're going to plug in the x based on what we're trying to find. Okay, so in part B, it wants us to find the probability of having 0 earthquakes in a year, 2 or 5 earthquakes in a year, one at a time. So we'll start with 0, which means we put a 0 in for those two x's. 0.93 goes in for the mean. Okay, we let the calculator do the work. There's a 39.46% chance that there will be 0 earthquakes on any given year. For 2, we just change those zeros to 2's. There's a 17.06% chance that there are 2 earthquakes in a year. And 5 earthquakes, that's a lot, right? There's a 0.23% chance. Example 2, if electricity power failures occur according to a Poisson distribution with an average of 8 failures per year, calculate the probability that there will not be more than 1 failure during a particular week. So first thing to note is that it's giving us an average across the whole year, but it wants us to find a probability for a given week. So we need to change our averages here. So 8 failures per year, switch this to an average per week. So we're going to divide that by 52 weeks in a year, and we get 0.154 failures per week. Okay, so we always want to start out by finding the correct mean if it's not given to us. All right, next up, we want to find the probability that there's no more than 1 failure, which means we can have 0 failures or 1 failure, or of course meaning addition. So now we just plug it in. 0.4 is our mean, 0.154 is our mean. 0 goes in for the x. Do the same thing for finding the probability of 1 failure. We get those two, and we add them together to get our answer, 0.9893. Example 3, a life insurance salesman sells on average 3 life insurance policies per week. Use Poisson's law to calculate the probability that in a given week he will sell some policies. So it tells us what the average is per week, and then it asks us about probabilities over a given week. That means that the mean is just given to us as 3. We don't have to do any math. All right, so when it's asking us what's the probability he sells some policies, that means he's selling 1 or more policies. In other words, it means he's selling at least 1 policy. Think back to chapter 4. Anytime we saw an at least 1 problem, what we wanted to do is 1 minus the situation where he didn't sell any policies at all. Okay, so we find the probability that he sells no policies. We plug that in, we get 0.0498, and that just gets subtracted from 1. So our answer, there's a 95.02% chance that he sells some policies. Part B, 2 or more policies, but less than 5. Okay, make sure you think about how these are worded. So 2 is good, 3 is good, 4 is good, 5 is not good because 5 is not less than 5. So 2 or 3 or 4. So here's our probability for 2 policies, 3 policies, 4 policies. Add those all up. There's a 61.6% chance of that occurring. And as the last thing in chapter 5, we're going to relate binomial distributions to Poisson distributions. Sometimes we can use Poisson distributions as a stand-in for binomial distributions to approximate a probability in certain situations. And namely, we have to have a large sample size of something greater than or equal to 100, and a small probability of success, where when we take n times p and we multiply them together, we get something that's smaller than or equal to 10. For example, in the Illinois Pick 3 game, you pay 50 cents to select a sequence of 3 digits, such as 729. If you play this game once every day, find the probability of winning exactly once in 365 days. This is really a binomial probability problem with a sample size of 365 since we're playing once per day, and a probability of success of 1 over 1,000 or 0.001. That's because we're picking a 3-digit number, and there's 10 options for each of those digits. 10 times 10 times 10 is 1,000. So we're going to plug all that into the binomial probability equation. Remember, this one was NCR, N choose R, P raised to the number of times we want to win, Q raised to the remaining 364 days. That gives us a probability of 0.2536. Now, since we have a large sample size, this is greater than 100, and since our probability of success is small, if we took these two things and we multiply them, we get something smaller than or equal to 10, we can actually use a Poisson distribution to approximate this probability. The thing we need for a Poisson distribution is the mean. We can find the mean with n times p. We get 0.365, and then we just plug that in with the actual x value we're trying to find, which is winning once. That gives us a very accurate probability of 0.2534.